Okay, I am back. I just essentially talked to myself for an hour making the second part of this and realized I did not press the record button, so I'm not really happy about that. Um, but we'll just do another take. Um, Honestly, that really sucks because that was a pretty good. I really went through that pretty well. But anyway, um, we're gonna punch. We're gonna draw. We're gonna push through this, and I'm gonna do this again. So anyways, we've done the Wilson cycle. We're going to move on from here. Large igneous provinces. All right. Man, I just went over this in so much detail. I'm so bummed I did not have that record button going. Anyways, in order to break apart a continent or split a continent one from the other, you need a driving mechanism, and it really needs to be powerful. And that's what lips do. Large igneous provinces. They are more than volcanoes. They are I mean, there are volcanoes associated with them, but they're the small part. These are gigantic underground magma plumes that come up under the crust of the earth and embed themselves there and wreak all sorts of havoc there. They actually begin to melt the crust. They begin to stretch it. They begin to open it, and they begin to force continents to separate. And when I say these things are big, they can be in the order of 2,000 miles long and 40 miles deep. They are just gigantic. And this is a cross section right here. You got the asthenosphere, lithosphere, crust, and you got a major plume coming up. It embeds himself under the lithosphere, begins to melt it, begins to take in pieces, and this ends up going up and embedding itself into the crust. It begins to melt the crust and take in the silica, and then it begins to punch through the crust in various different ways. And these little areas right here are perfect for creating minerals. These are like here too. You get minerals in here and along these. And these are dikes that come up on the edges. These are dikes that come up through the center. And then these are just sills, and then these are injections that get pushed horizontally through the crust. If you're looking down on plan view rather, you're looking down on this, G right here is represented to these round concentric rings right here. And the round concentric rings are basically caused because eventually this is going to deplete and then this is going to drop. And then the next time it fills up, lava likes to find conduits and it comes up through these side sheets right here, making these circumferential dikes. Just like this right here is represented to this. This is a volcanic eruption through this. This is silicic. It means it differentiated. It got crust in it. It got contaminated. Flood basalts are just basically primitive lavas, high in iron, formed very deep, very hot. These are differentiated. These little dots right here are kimberlites. They're just things that were injected into the crust and they solidified. Interesting thing about lips is that they have a tendency to start off as three joints at 120-degree angles, and then one rift begins to slow down or fail, and the other two just take over, and that's where the split happens. And this is a technical term for this is called an alocogen, and they're all over the place. The Amazon basin is an alocogen. It tried to break apart there, it didn't. Mississippi River is an alocogen. The St. Lawrence River is an alocogen. They are the if you look at Australia, they're down off of Tasmania or right off the southeast tip of it. There's a embayment there, and that's an alocogen where it tried to break apart. So basically, it's a failed area that wanted to break apart, but it did not. There are other ones along the East Coast, Connecticut River Valley, Newark, New Jersey, the Palisades Sill, that's one. The Newark one down in Jersey. Plus up in the bay, near the Bay of Fundy, there's one there. These are all over the place. And this is basically just those ones that are there that we can see that are not flooded with water. They're just failed. They didn't take off and they stopped. And I guess I did not see this, but you get carbonates in them, carbonatites. This is a very unique type of lava. It's a cool lava. And I'm interested to find out why that is. Maybe it's because the lava differentiates, it cools down, and then at the very end it solidifies to carbonatites. I'm not sure. But in any case, so these are lips. This is a in-your-face giant, you know, diagram of lip, 40 feet down, I mean 40 miles down, kilometers rather, huge mushroom-like area of fresh molten material, plume material right here. Then you have rest. This is where it starts to differentiate and contaminate. It's melting the country rock right here. So it's assimilating country rock. It's creating new magma right here, and then it's forcing its way up through these cracks. It is forcing the land to go this way, and you get those concentric dikes because this is going to eventually cave in, and there's going to be a depression there. So, and again, these are on the order of up to 1,000 miles or so. It's not like a volcano in Hawaii. Yes, they're low, they're domed, they've got calderas, but they are, instead of being the size of, say, Mauna Loa on the Big Island, they are all of the islands. You know, a couple hundred miles, even bigger. And interesting enough, you do see some of these features here in New Hampshire. There are injections. Those are just plutons. They're on a much smaller scale, but the principle is the same. And you see concentrations, certainly like bullseyes, when you look at them in Google Maps or when you look at structural maps. And those are just basically happened when we went over the New England hotspot. And in the Jurassic and the Cretaceous, and even in the Triassic, the Mesozoic, magmatic injections were getting forced under New Hampshire, Maine, and Maine, and basically creating these, and I believe also part of very eastern tip of Mass. There might be some there, and that chain continues out to the middle of the Atlantic, and then on the other side of the subduction zone. Tell me the subduction zone actually moves, but basically you had a situation like this, and there's I think one near Winnipesaukee, there's one in Ossipee, and there's another one that makes a small little hiking mountain in southeastern New Hampshire. I can't think of what it is, but in any case, you just erode all of this off, and just take all this off, and you're looking at a cutaway of what one of these looks like when you're looking at the Ossipee complex, or the Ossipee complex. That's the one that comes to mind. You can't miss it. The Castle of the Clouds is right in there. You can tell it's an oval-shaped thing, but that is a volcanic edifice. All right, so lips. Where do we find them? Well, everywhere. Lips are, the majorities are continental lips. Well, that makes sense because the ocean crust is less than 200,000 years old for the most part. There's a few spots that are older, but so any of these that are older that are gone. So the blues are oceanic lips, reds are continental. It makes sense that there's a whole bunch more, and then you have these silicic lips. These are differentiated lips somehow. I'm not exactly sure the entire cause of these. Even though this looks like in the ocean, it's not. This is considered continental crust. But what is interesting is that you got your Siberian one up here. This caused a massive, biggest extinction on the planet, really. This is related to Camp, which is a Central Atlantic Magmatic Province. So when Atlantic Ocean opened, it opened here, 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 and here. It took all of that to force these plates apart. And you have one here when India made its jolt across here. You've got them on the west. Then you're not going to see them because they're older, but you'll start to see them show up on other areas where there are continental breakups. So that's lips less than 3 million years old. Central Atlantic Magmatic Province. I didn't make that right, but it's supposed to be Central Atlantic Magmatic Province, Camp. And this is it right here. Boom, boom, boom. Huge amount of magma to bust those apart. So let's look at some lips. Lips in the last 500 million years. I'm going to go, after thinking about this, that these purple ones are intermediates because they seem to follow and they lie on arc areas. And island arcs in the ocean or ones that I know that have been slammed onto the sides of continents have a tendency to be intermediate, which means they're andesite and um, andesite and oh my god, I can't think of it. Gabbro andesite. I can't think of it. Gotta look that up. Andesite. What is the igneous outer part? Hold on. I apologize. I'm trying to figure out what the name of that is. Diorite. That's what it is. Diorite. I'm sorry. Sorry about that. Diorite. That's what I was looking for. All right. So these are very common on island arcs. Um, these are felsic, silicic lips. Um, and then, of course, you have the oceanic lips. And again, this is less than 5 million, so 500 million. So these existed. These are great tools for plate tectonics. You can see that these started together, and then as the plates split apart, they got stretched, or they basically these are the lines of time. So these were once together, but then they broke apart, and from the mid-ocean ridge, and they both went their separate ways. These are lips 500 to 1 billion. Probably some sort of arc up here, maybe an arc here. This is associated with the breakup. Actually, this is associated with the breakup of the Iapetus Ocean, Central Iapetus Mazatzal Province. Huge one in Australia here. By the way, these are excellent for rare earth minerals or metals and gemstones or what have you. Lips from 1 to 5 billion years ago, 1 to 1.5 billion. You got this was up here. This is a huge one. You got a giant one here in Amazonia. You got an Australian one. I think this is really good for mining too here. Like I said, any one of these can be really good. Kinewan, and this is the one that tried to break up the North America. 15 to 2 billion. Actually, there seems to be a lot of lips here. A few more silicics here. You got an arc one here, but the rest are all pretty much mafic lips. And 2.0, now we're back into the Proterozoic. Again, a lot of mafics. This is probably associated with a mountain belt here, maybe the Trans-Hudsonian, or maybe the breakup of it when it split. That's probably what this is. You got the Bushveld, huge economic value with that, but this is in the Proterozoic, and believe me, the Earth did not look like this at this time. This was here, spun 90 degrees, and this was flipped up again. I mean, it's just so different. All right, so now we're going to build North America, and in order to build North America, I have to bring together all these pieces of crust together, because I cannot do a geology of the East Coast without an area to stick it to. So everything that is in this area that's not blue or brown is considered the Craton. And the Craton, as I've stated earlier, is this assortment of primitive crust that came together, rifted, mountain ranges in between, it's sutured together, and then you have an island arc mountain range, another island arc mountain range, what was going to be a third island arc range, but it didn't quite make it. And then you have a continent-continent collision with Amazonia that produces the Granite-Ryolite Orogeny, and then the Appalachians were made after that. And of course, you have your western mountain belts. I'm not going to go into the West Coast because it's very complex, and that's for another conversation. And the gist of it is oh my God, what a mess, and it's true. Now, what you can tell here is that these ticks basically represent the higher crust. In other words, this piece of crust dove under. This piece of crust dove under. This piece of crust dove under. These may have moved side by side, but this came in and dove under. And this is the original Craton, right? This is the Craton right here. These are essentially pieces of primordial crust that end up getting welded together by this Trans-Hudson orogeny. So you've got Ray, Slave, Ray, Maine, Superior, Wyoming. Those are the that is the original that is the nucleus of North America. All right. This is the one section that I'm bummed that I got to do again because this was very complex. So we're going to do it. Each one of these lines represents a cross section, and the way we do it is it's A, B, and C. A, B, and C. So this is a line and represents A, and this is through 2.5 to 1.8. This is the Trans-Hudsonian Orogeny, and you're taking 3 pieces of primitive crust, and you brought them together. An open ocean basin opened up between them, and then it closed, and it made this mountain. This is the first continent mountain range of North America, I believe. So in cross section, you've got Slave, or the Wyoming province, I guess here. That's this. You've got the Superior province here, province, and in between, an ocean basin has opened up. And then in the middle of that ocean basin, one side began to subduct, and it looks like it subducted off to the east. And so it's going to build this island arc right here. So you have an ocean, you got an ocean, you got an ocean, and then you have continent, crust. And then you have oceanic crust, and then an island arc building right in between. So eventually these two pieces are going to collide, and they do. The crust, the oceanic crust continues to subduct. These two come together, they weld right here, and then there's the Trans-Hudsonian arc, now it's mountain range, and this has been sutured. And right in here, you have pieces of oceanic crust or stuff that was scraped off of it that basically gets faulted and scraped and metamorphosed, and so you get this sort of striped texture to it. Down here, we are now going to so on B, and this is what I don't like about this particular one, is that B does not show the Yavapai province here. It just shows the suturing. And then we jump to C, and it jumps way ahead. But that's okay, because what we're going to do is we're going to come down to here, and this is the accretion of North America in the middle Proterozoic. And so you got these pieces here. You got the Wyoming, you got the Superior, you got the Trans-Hudson right here, and then we're going to bend, and then you've got an island arc right here that welded onto this, and then you got an island arc here that dove under the Yavapai. The Mazatzal dove under that, which is this right here, and then you have the Granite-Ryolite Province, which is for one reason or another has begun to subduct down to the east, and then you have the Granville right here. But as this is happening, this plate right here ends up, the oceanic crust goes down, and it begins to melt and produce magma, and it comes up and through here, but it never ever completes the cycle. It just injects granite, rhyolites, and very felsic materials. It's as if the plume came from underneath, and it punched up into the crust, but it never really made it through, or it never it never thinned the crust up enough to start producing oceanic basalts. So it just stopped. And so we know that a piece of that there was subduction going this way off to the east from this. And my guess is that what happened was this subducting piece began to pull this piece off and stretch it, and decompression melting put tons of plumes up under here, but it was not enough to fully pull it away. And then stretching stopped, and then Amazonia came in and stopped that and crunched it to make the Grenville. So we're going to see it on the next thing. So now we're at 1.3 to today, and we're going to look at D. D is an interesting one, because what it does is it shows you got your Wyoming, your Trans-Hudsonian, you got your Superior. Now you got this thing right here. This is a plume that came up underneath this crust, and it ended up making this rift right here, and it erupted for about 20 million years. And this was actually, it actually comes over here too. As I said, there's usually 3 different, I would imagine the third one would up here somewhere over here. But this tried to break apart the crust, but it did not. And so this actually fails after about 20 million years. And again, you've got your Kiwanian Rift here. You got your Yavapai. You got your Mazatzal. You got your Granite-Ryolite Province, and you got your Grenville, which is right here in the red. And again, I don't feel that this is 100% accurate, because I think there should be a subduction zone going down under here, but I'm not going to get into that. So now we come down to E. And E is showing the accretion of the Appalachian Mountains. Now, they are represented right here by the blue, and they are represented right here. So let's go all the way through now. Wyoming, Trans-Hudson, Superior, Rift, right there, boom. Yavapai, Mazatzal, boom, boom. Grenville, right there, we got it right there. And then we have the Appalachians, and the Appalachians are coming in and subducting under, and this is the plate of the Appalachians subducting under. This oceanic crust has been faulted and thrusted, and that's why you see these different, this sort of like banded technique, banded design here. What's interesting is it changes color as we go. It's funny that you can see that this right here has now been subducted under here, and then these begin to change color the longer we go, because they're getting heated and compressed. So now we get down to F, and this is the whole thing. This is right here. We got the West Coast, which is the Sierra Nevada. We got a plate going underneath this Farallon plate. We have got something here. It's a drip. I don't know. It's maybe a slab breakoff. We got the Sierra Nevada Basin and Range. We have the Yavapai. We get the Wyoming, the Trans-Hudson, the Superior, the Mid-Continental Rift, the Yavapai, the Mazatzal, the Granite-Rhyolite, the Grenville, and then the Appalachian crust right here going under, and then the Appalachians. And now Africa has now gone away and rifted away. And you can see we created more continental crust. But this is what you would basically expect to see under the North America right now. That is what it looks like. So it's a series of accretions and mountain ranges that have all been ironed out, and probably there'll be another one. All right, so thank God I'm recording, because I don't know if I can do it a third time, but I need to build North America, and I'm going to do it right now. And so the original the original Cratons are listed here in gray. These are the first ones. They are greater than the Archean. They are Archean in age, or 2.5. And I put this little bullet here, or whatever symbol, to let you know where we are present day. That's Gunquit. So what's interesting here is by about 2.5, and this is why we changed tunes from the Archean to the Proterozoic, is we start to see evidence of passive margins, and that's what these yellow spots are. These are passive margins, and these are very important, because this is showing that there is erosion going on, and more importantly, silicic materials are coming out, and these are important because that means that there's weathering and rocks are breaking down. Now, the question remains, were these together and opened, or were they just apart and they closed, forming the Trans-Hudson? I don't have an answer for that, but all I know is that these pieces seem to fit quite nicely. So my guess is that maybe the Trans-Hudsonian broke up. I don't know, but you can obviously see that these pieces could easily fit. Like this would go to here, this would go to here. So that's up to some scrutiny. All right, first juvenile arcs, 1.96, 1.92, developed along the Slave Ray collision zone. This is called the Thelon arc. This is way up here. We've got our sediment still here. But whatever the case, back around 2 billion years, this rifted, or actually it just came together, or rifted off of here, and you get an island arc that slams into this. So for whatever reason, it went up between here. I don't know if that was originally the plan, but this definitely was a rifted margin, ocean basin closed, and an island arc wedged onto that. But it also seems like it went right up here and it sutured these two pieces together. All right, closure of oceans, 1.92 to 1.86. So we have more action going on here. So now we have another arc, an ocean basin that opens up off the edge of this. Another island arc comes in and closes that. So you've got this right here. You have a small arc right here. You've got a small arc right here, and you've got some sort of small rifting events right here. But these are all juvenile arcs. They are all very young, and they're relatively small, but they are juvenile lavas that are basically coming. They're erupting to the surface, and then one piece of oceanic crust is diving under another, and you create these juvenile arcs, and they are andesitic or dioritic in composition. They're not rhyolites, they're not granites, they're not mafic rocks either. They're in between. So now we start to have more accretion to microcontinents, continued with the Narasimhajuk arc, and the final suture of the Great Bear arc along the Yavapai origin, which is 1.86 to 1.84, and then the early sutures of Archean Orogeny. Okay, so I'm not exactly sure where the Great Bear arc is. Oh, it's up here. Great Bear arc, yeah. So again, more action up here. It looks to me like stuff is being driven this way because this is a thrust fault. So whatever's happening here, there's something closing or something coming together here, and it's forcing arcs to come into here, and it's actually thrusting under this this piece of crust right here. And you have another one here. You got the Pinocchian. This is a small mountain range that sort of forms off of the south coast of the Superior Province. Again, small rifts. All right, Trans-Hudson Orogenic Belt, 1.84 to 1.82. Now this is a major orogenetic episode. These two pieces came together, and when they did, they crunched the ocean in between. The ocean subducted on both sides. Actually, this piece of crust got stuck in the middle, and it created a mountain range that was, probably at least 20,000 feet high, and it it crossed the entire continent or the proto-continent of Laurasia. So it was a big deal, and it's a huge suture that welds basically the center of North America together. And again, we got some more juvenile activity, some more sedimentation. Something's going on down here, not sure what. Now we're going to accumulate more arcs, and it's like, this is becoming a broken record. Things are just repeating themselves. There's going to be more rifts, more arcs, like something split right here, yeah. All right, so now we are into the Mesoproterozoic, not the Paleoproterozoic, and we have our first our first signs of juvenile oceanic arcs, different from these. These are the Mesoproterozoic, and they are represented in green. And there's basically an ocean here that's beginning to close. You've got some subduction zones that have formed, and they are just starting to accumulate sections of oceanic crust and lift it and then bring it in. These are more continental arcs. This is a purely oceanic arc, I believe. Now, the Yavapai province is largely an assembly of oceanic arc terrains, 1.76, 1.72 in a very complex area. And they eventually, I mean, you've got arcs, you've got, I mean, you've got crust. It's a mess. And this ends up, all these arcs and this crust end up subduct underneath the Superior province and the Wyoming and weld onto here, and they stay. And that is one of the first full arc mountain ranges to happen in the Mesozoic in North America. I'm sorry, the Mesoproterozoic. Let's see, Paleoproterozoic to 1.2.5 to 1. I always mix this up. 2.5 to 1.6. No, we are still in the Paleoproterozoic. All right, and then 1.6 to 1.0. All right, so we are still in the Paleoproterozoic here. The Meso does not start until 1.6. But anyways, this is a major mountain range event, and it's all really mostly oceanic. All right, so once you have cried the arc ends up suturing onto this, and of course you get plumes and you get intrusions under the island arc once it matures, because a new subduction zone forms and it starts intruding magma up into the arc, and it actually ends up more or less stitching it together and making it a solid entity. So these are represented by these yellows right here, and this is the beginning of new arcs that are going to start coming towards this. And that is in the form of the Mazatzal Province, 1.69, 1.65. It's very well documented in the Southwest, Arizona, New Mexico. It's all there. And so the Pinal and the Laura Manzano group come together. The small out groups also occur in north. See, this is interesting is that this actually is a couple of pieces that kind of show up here, and I don't know why that is. I don't have an explanation for that. I haven't read anything about it either, but it's interesting that you'd have pieces of this that would show up way over here when this is clearly very far away. Unless this, when it ripped it apart, there was just a piece of it that was left. I don't know, but it's very interesting that piece would be there. And so you've got two island arc episodes here, mountain building events, and this one's even bigger. It stretches the whole from the top of Newfoundland all the way down to Baja California. It's a huge mountain range, and again, primarily oceanic in origin. And then around 1.55 to 1.35 billion years, extensive juvenile terrain extending from the southwest United States to the mid-continent appears. And what I feel happened, and you shouldn't use those words in science, but I've never had a full grasp on this. I mean, you've got two full Wilson cycles right here, and then you have an area here that begins to do the same thing. And in the initial stages of a Wilson cycle, you end up getting plumes under here because of the crust extending, and you really thin the crust. But as you do, you're releasing pressure underneath it, and the mafic lavas come up and they embed themselves in the crust, and they begin to assimilate and melt the crust, and they begin to produce at first very silicic, granitic, plutons and rhyolitic lavas. And so what I think happened is a rift zone opened here, and it began to subduct east, and it began to pull this apart. And then probably the same thing happened here. It just was able to complete. But for some reason, it stopped. And I'm wondering if it had something to do with the arrival of Amazonia coming, and there just was no place for it to go and finish. But in any case, this is a huge area, lots of granites, lots of lava, but no mid-ocean ridge basalts. So it stopped. So this is an incomplete Wilson cycle. And then, once this, as this was going on, A-type granites ended up getting injected into here, and I think that makes sense. Along with that, is that as it was stretched, the magma melted the crust, the granites got intruded, and this ends up stitching this whole thing together and locking it. So it's a very interesting thing, and it's as if it didn't just happen here; it happened, further back. So it wasn't just here, and I don't know. It feels to me like there's something subducting under this that would have caused this. I don't know. But why would it have intruded so far back? And it could be the arrival of, the Granville Orogeny. But the Granville Orogeny does not really start for another. It's going to be close. But this was way before that. That's almost, couple million years early, at least, what, so 1 it's billion. At least 100 million. Yeah, I mean it's weird, and I don't understand why exactly that. All right, so most significant plutonic event, 8 times granites that stitched them out, blah blah blah. So yeah, it injected everything. So for whatever reason, there was some action going on here, and it caused a lot. Maybe when this thing was being stretched, it also stretched here. I don't know. It's very possible. All right. Here we are, the Granville and Llano provinces, 1.3 to 1.0. These represent the culminating continent-continent collisions that assembled Rodinia. And it is represented by the red here. Really, it was a much larger thing, but, it's been separated, eroded, whatever. But this was a major this may have been the biggest mountain range in Earth's history, because it was gigantic and it circumnavigated the globe. And that's represented in red right here. These are the Adirondacks. Why in the hell is that there? I have to fix that. Fuck. All right. I am going to fix that right now. That just is bothering me. I don't know why that is. All right, apologize for that. I had to fix something. But yeah. And the Granville Orogeny, that represents the suturing of Rodinia. And the continent, Laurasia, will stay locked in this area for almost, at least 400 to 500 million years will be locked. So once this occurred, this is a major orogeny. And then when the Granville Orogeny begins to break up, or when the continents separate, Amazonia decides to leave, we get a massive amounts of injections trying to come in to separate it, and you get plutons stitching together this particular orogeny too. And these plutons show up all over the place. So, like I said, this was a major event. And then the final phase of rifting detached a Argentine pre-Cordillera microcontinent from the Ouachita, Texas embayment region of southern United States around 535 million years ago. This pre-Cordillera terrain is currently located in western Argentina, and that's true. That's how we knew that this was that Rodinia was the mystery continent. I mean, South America was the mystery continent that ended up being sutured to North America. And you can see here, These are rifts that just opened up as the Amazonia tried to get away. And it just littered and just diced everything. So very, very complicated geology here. And we will end it right there for part 2. And then I will go through the supercontinents when we get back. And I will talk to you soon. Aloha.